Hello everyone, welcome to the course Design and Analysis of Algorithms. You are watching Knowledge Spade. In the last lecture, we have defined the kinds of analysis. We have also considered few examples to make the concepts clear, that what is worst case analysis, what is best case analysis, and what is average case analysis. In today's lecture, we are going to define the asymptotic notations. We will see what is asymptotic analysis, and by considering few examples, we will try to make the concept clear. So let's start. Asymptotic analysis. In asymptotic analysis, we ignore the machine-dependent constants. In the previous lectures, we have considered few algorithms and we have constructed the complexity functions. In the complexity functions, there are some coefficients and constant terms. Those coefficients and constant terms basically depend on the machines. These are machine-dependent terms. So in the asymptotic analysis, those terms are ignored. Secondly, while we are analyzing our algorithms asymptotically, we look at the growth of the function, the function t of n, as n approaches to infinity. It means we are considering the growth of the function, that how this function will grow when the value of n grows larger and larger and larger. That is, when the value of n is very high, what will be the behavior of the function t of n? This is asymptotic analysis. Basically, this term, the asymptote, came from the mathematics. In mathematics, an asymptote is a line basically that approaches to a curve at infinity. We can say that a line is an asymptote to a curve if the distance between the line and the curve approaches to 0 as the x or y are both approaches to infinity. Even in another way to define the asymptote, that an asymptote is a line that is a tangent to the curve at infinity. Okay, before we will discuss the asymptotic analysis, we have to define some notations or functions. These notations are big O, big omega, theta, little o and little omega. These notations or functions will be used to analyze the algorithms asymptotically. Most of the time, we consider these three notations. And out of these, the big O is probably the most frequently used notation. As you will see in this course, most of the time we will discuss the big O notation. So we will define these notations and then we will take some examples. I think it is more appropriate to first look at the growth of the function, that what is mean by the growth of the functions. So what is mean by the growth of the function? Let's take our first example. In this example, we have two functions. The first function is f of n and the second function is g of n. The first function f of n is equal to 100n plus 200 and the second function, that is g of n, is equal to 6n square. Let's consider some values of n and find the values of f of n and g of n. So we will start from the 0. Take the value of n is equal to 0. When we put n is equal to 0 over here, we will get 200. And when n is equal to 0 over here, we will get answer 0. The next value of n is 1. Assign 1 over here, we will get 300. And when we will put 1 over here, we will get 6. As you have seen, this function is greater than this function for the values 0 and 1. Now take the value of n as 2. When we will put 2 over here, we will get 400. And when we will put this value over here, we will get 24. For 3, this function is 500 and this function is 54. And so on. When we will take the value of n is equal to 10, this function will be 1200 and this function will be 600. For all these values, as you have seen, this function is dominating this function. This function, that is f of n, beats the g of n, that is 6n square. Okay, move ahead. Suppose we will put n is equal to 20. When the value of n is 20, the value of f of n will be 2200. and the value of g of n will be equal to 2400. So at 20, this function beats this function. That is, g of n now is greater than f of n. When we put 100, the f of n will be equal to 10,200, while the g of n, this function, will be equal to 60,000. As you have seen, when the value of n is 100, the difference of g of n and f of n is about 50,000. So from this we have concluded that for the smaller values of n, the function f of n is greater than g of n, but when the value of n increases, the value of g of n is greater than the value of f of n. Let's look at the graphs of these functions. The blue line represents the f of n and the red line represents the g of n. As you can see, the g of n is below the f of n until the value of n reaches near to 20. So as you can see over here, the function g of n beats function f of n when the value of n reaches near to 20. What's that means? It means the growth of the function g of n is much greater than the growth of the function f of n. Let's take another example. Once again, we have two functions. The first function is f of n is equal to 1000 n plus 2000, and the g of n is equal to 0.6 n square. If you compare these functions with the previous example, you can see the coefficients over here are increased while the coefficient over here is decreased. So let's see how these functions behave when these coefficients are very high and this coefficient is very small. We will compare these two functions by taking few values of n. As you can see, the values of this function are much greater than the values of this function for small values of n. Let's take the value of n 100. At 100, this function will be equal to 102,000, while this function will be equal to 6,000 only. So once again, the value of this function is much greater as compared to this value. Next, take the value of n is equal to 1000. The value of this function will be 1,002,000, while the value of this function is 600,000. Once again, the value of this function is much higher, much greater as compared to this value. So now take the value of n 10,000. When we will put 10,000 over here, we will get this number, that is 10,002,000. While when we will put this value over here, that is 10,000, we will get a value that is 60 million. Now compare these two values. You can see the 60 million is much greater as compared to 10 million. Here's the difference is about 50 million. Once again, we have concluded that this function will beat this function asymptotically. What is mean by asymptotically? It means when the value of n grows larger and larger and larger, ultimately there will be some point when the function g of n will beat the function f of n. This is basically a linear function and this is a quadratic function basically. Now, as you can see in the graph of these functions, the function g of n, that is represented by this curve, the function g of n beats the function f of n at some value which is greater than 1000 and less than 2000. And when the value of n is 5000, the value of f of n is just near to 6 million, while the value of g of n is 15 million. So what we can conclude from this example? We can see the growth of this function is faster as compared to the growth of this function. In other words, the growth of this function, that is f of n, is slower as compared to the growth of this function. in asymptotic analysis, it is the growth of the functions that matters. So here's the definition of big O or lower bound notation. Consider a function f of n which is non-negative for all integers n greater than or equal to 0. We say that f of n is equal to big O of g of n, or in other words we can say f of n is in big O of g of n, or even you can say f of n belongs to big O of g of n if there exist positive constants c and n naught such that f of n is less than or equal to c multiplied by g of n for all n greater than or equal to n naught. So this is the definition of big O. As you can see in this graph, we can say that f of n is equal to big O of g of n if the behavior of the function f of n and g of n is in a way that whatever the initial values of these two functions, but there will be some point so that the function g of n will always dominate the function f of n after that particular point, and that particular point is called n naught. You can take this point as n naught, or any point greater than this point can be taken as the point n naught. So after point n naught, this function g of n will always dominate the function f of n. Formally, we can define big O as big O of g of n is equal to set of all f of n's. So it means this function, the big O of g of n, is basically a class of functions, a family of functions, a set of functions. So therefore it is equal to set of all functions f of n, set of all functions f of n such that there exist positive constants c and n naught such that the function f of n is non-negative and it must be less than or equal to this function for all values of n greater than or equal to n naught. Therefore we can say the meaning of big O of g are the set of all functions that grow no faster than g, like this function. So the growth of this function is not greater than the growth of this function. Therefore we can say f of n is equal to big O of g of n, like over here. Let's define the omega notation. Consider a function f of n which is non-negative for all integers n greater than or equal to 0. We say that f of n is equal to omega of g of n, or f of n belongs to omega of g of n, or f of n is in omega of g of n if there exist positive constants c and n naught such that f of n is greater than or equal to c g of n for all n greater than or equal to n naught. So in the definition of omega, the only difference is this inequality. In the definition of big O, this inequality was f of n less than or equal to, but now it is greater than or equal to c g of n. So this is the only difference in the definition of big O and omega. So therefore it is called the lower bound notation. In the big O, the growth rate of g of n was not less than f of n, but now the growth rate of g of n is not greater than f of n. So this is the difference. Omega of g of n is equal to set of all f of n such that there exist positive constants c and n naught such that f of n is a non-negative function and f of n is greater than or equal to c g of n for all n greater than or equal to n naught. So it means we can say the big O of g means the set of functions that grow no slower than g. As you can see over here in the graph, as you can see, whatever the initial values of these two functions, but after some time there is a point n naught that after that point the function f of n always beats the function g of n, c g of n. In this case we can say f of n is equal to omega of g of n. The growth rate of f of n is greater than or equal to the growth rate of Cg of n as mentioned over here. Our next definition is for theta notation, also known as the tight bound notation. Consider a function f of n which is non-negative for all integers n greater than or equal to 0. We say that f of n is equal to theta of g of n, or f of n belongs to theta of g of n if there exist positive constants c1, c2 and n0 such that c1 multiplied by g of n, this function will be less than or equal to f of n, and f of n will be less than or equal to some other constant, that is c2 multiplied by g of n, for all n greater than or equal to n naught. So over here a function that is g of n becomes greater than f of n for some constant, and it becomes less than f of n for some other constant. So this definition is for theta notation. Formally, theta of g of n is equal to set of all functions f of n such that there exist positive constants c1, c2 and n0 such that f of n is greater than or equal to c1 g of n and less than or equal to c2 g of n for all n greater than or equal to n0. What's that means? The theta of g of n means the set of all functions f of n such that these functions grow like g of n. That means all those functions whose growth rate is similar to g of n. As shown over here in the graph, that after a constant n0, the behavior of these functions is so that the function f of n is less than or equal to g of n when it is multiplied by a constant c2, and this function is greater than the function g of n when g of n is multiplied by another constant, that is c2. So in this case we say that the function f of n and g of n grow in a similar way. Now we will take some examples so that we can understand these definitions in depth. So before we start the definition, let's make it clear that the definition of theta basically include both the conditions that we have already discussed for big O and big omega notations. For example, the condition over here, the first condition, it is the same condition that we have defined in the omega notation, and the second condition, that is this one, this condition is same as we have defined in the big O notation. So if the both conditions hold, that is the condition for big O and the condition for omega, if the function hold both the conditions, then we can say the function f of n is equal to theta of g of n. Now let's look at few examples. These two functions have already discussed when we were talking about the growth rates. As we have seen that the growth rate of this function is greater than the growth rate of this function, and this function, that is g of n, dominated this function which is called f of n when the value of n is greater than or equal to 20. So by this we can write that this function, that is f of n, is less than or equal to this function, that is g of n, for all n greater than or equal to 20. That is, for all values which are greater than or equal to 20, the function n square, when it is multiplied by 6, dominates this function. Now this is the condition that we have defined in the big O notation. So over here the value of c is 6 and the value of g of n is n square. Therefore we can write f of n is equal to big O of g of n, where f of n is this function and g of n is this function and the value of c is 6. So by definition we can say f of n is equal to big O of g of n. How we can prove that this function basically belongs to big O of n square? We will prove this in the next part of this lecture. Remember, this lecture consists of two parts. Let's look at the next example. This is also the same example as we have already discussed. As we have seen that this function once again dominated this function when the value of n is greater than or equal to 2000. So by all the discussion that we have already made while we were discussing the growth of the functions, we can conclude that this function that is called f of n is less than or equal to the function g of n that is called n square multiplied by 0.6, and this is true for all n greater than or equal to 10,000. Basically, this function dominates this function after 2000, but you can write over here 2000, 3000, 4000, or any number which is greater than 2000 can be written, because if this condition is true for 2000 and greater values, then obviously it is true for 10,000 and greater values as well. Now, as this condition is true, so by the definition of the big O, we can write that f of n is equal to big O of g of n, where g of n is n square and the value of the constant c is 0.6. So therefore, this function belongs to big O of n square class. Let's take another example. This is basically an interesting example. The interesting thing is that both the functions are basically quadratic function. Over here, the function f of n is equal to 2n square plus 3n plus 1, while our function g of n is equal to just n square. If we take the value of constant c is equal to 3, then it will become 3n square. Now we will put the values of n from 0 to 6. For 0, this function is 1 and this function is 0. When we will put various values, we get these values for this function and these values for this function. As you can see over here, when the value of n is 4, the function f of n is 45, while the function g of n is 48. The value of this function dominated this function, and after that, when you will put 5 or 6, you can see that this function always dominates this function. Therefore, you can say the growth rate of 3n square is greater than or equal to the growth rate of this function. By this, you can write that the function f of n is less than or equal to the function 3n square for all n greater than or equal to 4, as shown over here. So as we know that this is the condition of big O, so we can write that the function f of n is equal to big O of n square. So we will stop over here. This is just the first part of our lecture. The next part of this lecture will be very important to understand these definitions.